Hi everyone and welcome back to PrepFusion. I am Anish and today we'll start our chapter 2 of electrical machines. So chapter 2 will be DC machines. Now this chapter is only for EE guys. IN aspirants can ignore this chapter. They can start with chapter 3, that is induction machines. So this particular chapter is only for EE, right? Because in the gate syllabus only for gate IN syllabus only induction machine and transformers are there. I have seen the gate IN syllabus, it is induction machine and transformers. If it gets changed, then of course you need to study this as well. But as far as I know, currently only transformers and induction machines are there. Okay, so this will be for only EE. You can see the picture here. Some kind of coil is there, which is providing some flux. This flux is uh, like provided to a machine. Okay, so I hope in your college you have very basic idea about DC machines. So we will try to understand all those concepts and we will try to nullify all your misconceptions, right? Or whatever misconceptions you had, we will clear all those with basics. And trust me, the content that I am bringing you is the best content. You already know that after studying the transformers, you know what kind of content it is, right? I hope you have compared with other places and you know what kind of content I am giving over here and what kind of content other guys are giving, right? So you guys already know the balance. So this will be the same only, but DC machines will be much more easier. Why? Because it is DC, right? And you know calculations in DC is very easy because everything is constant. But remember, even though it's a DC machine, there is bit of AC in the machine. We will discuss about that. So in today's lecture we will discuss about the basics of DC machine, basic like what things are there in a DC machine, not exactly the construction but bit about the things. Then induced EMF. Okay, what is the like brief formula for induced EMF? I will not completely derive it, but I will discuss the induction behind the induced EMF and the different types of DC machine. There are many types of DC machine. In transformer we had only single phase and three phase transformer. DC machine has multiple types of transformer depending upon how this field winding is excited, right? How this field winding is connected, the types also changes. So let's first discuss bit about about what does a DC machine look like. So a DC machine is nothing. This is just the body of the DC machine, right? This is just the yoke. Okay, it's called as the yoke. Don't worry, we will learn about construction in after 2-3 lectures. But just to give you give you an basic idea, this is the yoke, and these are actually are the poles, right? These are the poles, north, south poles, and in these poles, what we do, we connect the windings. So here, like some kind of roughly I will draw some kind of windings are there. These are known as the field windings. Okay, these are known as the field windings, and inside this yoke, right, there is this rotor. This is known as the stator portion, and this, right, is the armature. Actually this is called the armature. This is called the armature. So in armature what happens, I'll just write here. In armature, it is just a placeholder for conductors. It is just a placeholder for conductors. So these are the conductors, right? These are the conductors. Conductors. Now what happens? Conductors also carry some amount of current. Conductors also carry some amount of current. That's why the name conductor. They will carry some amount of current. Now if they are carrying some amount of current, and here, right, I have field winding. So north to south. So what will be the direction of the field for the pole field winding? Direction will be somewhat like this, north to south, right? This will be the direction of the field. So I have a magnetic field and I have a conductor, so it will experience a force, right? So if I have a magnetic field and a conductor that is carrying a current, conductor that is carrying a current, then what will happen? Then there will be force experienced by the conductor, right? Fleming's left hand rule, right hand rule, we will discuss about that. There will be a force, and due to that force there will be rotation of the armature in any one direction, either in the right clockwise or anti-clockwise. So due to the force there will be rotation. So this is the basic phenomena that we will work in. So the armature is actually the rotor, the part of the DC machine that rotates, and the field windings or the field is the stator. Field winding of the field is this portion is the stator, right? This whole thing is the stator. This will not rotate. So just giving you a brief idea, right, about a DC machine, how a DC machine works. So DC machine can work as a generator or a motor. Whenever the term DC machine is there, it can both work as a motor or a generator. It depends how we want to use it. So we will discuss about different types of DC machine, all those things we will discuss, right? So let's classify our DC machine. So there are two types of current in a DC machine, as I mentioned, right? So there is a field winding and there is this armature winding or armature conductors. So both of them carry current. Field winding also carries field current, armature winding also carries armature current. So sometimes this, so that's why these are the two currents. So this armature current or the also known as the load current, armature current. Armature current or the load current, right? So this is the current run by the external circuit or load connected to the machine. Okay, that is connected with the conductors. It varies depending on the load demand. So it is also called load current because I connect the load with this conductors. Armature is directly connected to load. Now you might have a doubt, sir, if this is rotating, how will I connect a stationary load, right? So for that, if you see, there are here brushes and commutator. So we will learn about this, that our load is stationary, but this portion will keep on rotating. We will discuss about that, don't worry. Okay, so this is the load current basically, which will be directly connected to the load, or I will also known as a supply current, which will be directly, like supply current will provide this armature current, right? We will discuss about this. Field current. Field current is also known as the exciting current or the magnetizing current. It is responsible for developing the main pole field flux. So this flux, right? This flux, who is responsible for this? The field windings, the current in the field windings. So the current in the field windings are known as the field current, right? Also known as the exciting current. Why? Because they provide the exciting phenomenon, right? If this field current are not present, then this magnetic flux will not be there. If this magnetic flux is not there, that means there will not be any force, because simple Fleming's rule, right? There has to be some like magnetic force, like right hand Fleming's right hand rule, Fleming's left hand rule. You know, if force direction is like this, then what will be the, sorry, if the current direction is like this, magnetic field direction is like this, then force will be here, something like that, right? I hope you remember. We will discuss that as well in this lecture only. In this, not in this lecture, later on. So don't worry about anything. Okay. So yeah. So field current are responsible for providing the excitation. So in DC machine, remember, the field current will always be DC in nature. In DC machine, field current always will be DC in nature. But remember this armature current, right? Although it seems like it is DC, but actually it is not pure DC. It can be pulsating DC, right? So yeah, that we will discuss about that. It can be pulsating DC. So, and the whatever EMF that will be induced here, right? It will be pulsating DC. It will not be pure DC, right? I know there is a misconception that this is pure DC. It is not pure DC. It is pulsating DC. We will discuss about that. Okay. But in case of field winding, the whatever current will flow through the field, it will be pure DC. So I hope you know how a flux is generated. So if it's a pure DC, right? It's very simple. So flux will be Ni upon reluctance. This is what we have learned in transformers. Very basic thing. So this is the flux that will get generated here. Okay. Now coming further, so my field winding can be further derived, like zoomed in like this. So remember, you have to remember what direction you will give to the field winding, right? That also you have to understand. So here, if I see that if the current direction is like this, can you tell me what will be the direction of the field? So this also we have learned, right? I will simply use the right hand curl rule. If I curl my fingers, along the, direction of the current, I see it is going in the left hand side. So the direction of the field flux will be on the left hand side, right? So same thing, field winding is the stator portion and armature winding is the rotor portion. So it will, armature winding will be placed in the rotor, that is the load current, and field winding will be placed in the stator, right? Now in case of, like, we will learn about another machine that is known as induction machine. In induction machine there is no like field winding and armature winding. It is a singly excited machine. In DC machine and in synchronous machine, so in DC machine and in synchronous machine, It is a doubly excited machine. Why it is a doubly excited machine? What do I mean by doubly excited machine? Doubly excited machine doubly excited machine means that I will provide the excitation to both the field winding and the armature winding. In induction machine there is nothing like armature field winding, but in synchronous machine there is again a field winding and kind of a armature winding. We will discuss about that when we will study synchronous machines. That is the important portion here, right? So that's why doubly excited, because I am exciting both the windings, the armature winding and the field winding, because current is flowing through both the windings. Okay. Uh, Now, in case of armature winding, please keep in mind here the current will be DC, right? DC voltage. Across the field winding, there will be DC voltage. But remember, in the armature winding, right, AC voltage is induced. How it is induced AC voltage? I will discuss about that. So in armature winding, AC voltage is induced. But what you do? But what we do is we basically rectify this voltage, right, to DC. There is a mechanical rectifier known as commutator. Mechanical rectifier. Mechanical, why? Because it is a physical rectifier. It is not an electronic rectifier, just like a what do you say, a bridge circuit like diode rectifier, right? It is not like that. It is not an electronic rectifier. It is a mechanical. Like physically, it will be there. Physically, mechanical rectifier. That will what? That will convert this AC induced voltage into DC voltage, right? Will it be purely DC? No, again, right? Whenever we convert a sine using a diode rectifier, we see it's a pulsating DC, right? DC will be something like this. Here also something similar will happen. It will not be a pure DC, it will be a pulsating DC. Pulsating DC. So I'm just giving you a overview. We will go through each one of them slowly. I'm not proving anything, just giving you a overview. Okay. Now let's discuss about the torque production, right? How torque is produced basically. How a torque is produced, we will discuss about that. Okay. So if I see, I have these three cases and we will try to decode these three cases one by one. We'll try to decode these three cases one by one. So let's take the first case, right? If I have the stator coils and the armature, let's say armature coil is placed here in the case one. A armature coil, a conductor is placed here, right? And only the stator coils are excited. So if only the stator coils are excited, let me like the direction of the currents are also given, right? So in there current is going incoming and in the top current is outgoing, right? So if I just curl my fingers along the direction of the current, the field is along the right hand side. So this is the north pole, then this will be my north pole, this will be my north pole, and this will be my south pole, correct? So field direction will be somewhat like this. Field direction will be somewhat like this. This will be the field direction. Now a conductor is placed here. Will anything happen here? Nothing will happen. So of course, if they are not carrying any current, right? I know like there was some force equation. If we have studied a bit of EMFT, F equals to BIL sine theta, something like that, right? I will derive it as well. That F is equals to some product. F is proportional to B, the magnetic field across the conductor, and the current across the conductor, multiplication of the current, right? So here there is no current in the conductor. If there is no current in the conductor, there will not be any force. So here the force is zero. When there is no excitation in the rotor coil, only there is excitation in the stator coil. Now let's go into the second case when there is excitation in the rotor coils. So if I have a conductor and there is excitation in the rotor coils, what will happen? So if there is excitation in the rotor coils, right, basically it will produce a magnetic field. What will be the direction of magnetic field? Now my thumb will be direction of the current. So I see it is a dot is towards me. So it's a dot is towards me. So direction of the fingers will give me the direction of the magnetic field. So it is in the anti-clockwise direction, right? Anti-clockwise direction. So the direction of the magnetic field will be like this, in the anti-clockwise direction. So it will cut the field windings, right? It will cut the field windings, but again, what is the problem? The problem is this time the field windings anyways is a stator. It anyways won't move and it is not giving out any magnetic field. So again, nothing will happen. They will not rotate at all. Okay, no rotation, no rotation. No rotation. Okay, nothing will happen, no rotation. Now let's jump into the third case. If I now observe the third case, in the third case, what will happen? In the third case, very interesting that both the rotor and the stator both are excited now. Both are excited. So if both are excited, what will happen? If both are excited here, in this case, if both are excited, okay, if both are excited, then again a field will be generated from here to here, same direction, right? If I just curl my fingers of that direction of the current for the field winding, curling my fingers, so this is going inwards, this is coming outwards. So inwards, then outwards, right? Top is outwards, bottom is inwards. So it's like in the right hand side, right? For this case as well, it is right hand side. So this will be the north pole, this will be the south pole, correct? Now the conductor is also carrying a current. If the conductor is also carrying a current, it will also, like it has a current, it will also generate a field. This will also generate a field like this, right? Clockwise direction. So these two fields, right, will interact with each other. This you have, I think, will be studying in measurement as well. And if I have two magnetic fields, right, or let's say if I have a current carrying conductor across a magnetic field, it will experience a force. It will experience a force. Now what will be the direction of the force basically exerted? So if I see that initially the magnetic field was in this direction, right? So the field pole will try to keep the same direction. But here what is happening, the magnetic field, right, I see it is somewhat changing. So the resultant magnetic field is somewhat changing here, right? Because I have a magnetic field here as well. So resultant magnetic field here will be somewhat like this, correct? Somewhat like this if I have a single conductor. So of course our like this field excitation will not like this, so it will try to revert back to its previous state, because we know no one likes sudden changes. So it will try to apply a force in this conductor, that this conductor moves in the upward direction, so that it goes out of this field, right? It goes out of like this field does not affect this field flux, I mean this field due to the armature does not affect the field windings. So it will try to give a force in the upward direction. Okay, it will try to force the conductor in the upward direction, so there will be rotation in the upward direction, right? If I have a single conductor, okay. Now same thing is here only. If I have two conductors now, if I have two conductors, so here the field direction will be somewhat like this, it will be somewhat like this skewed, because this is in the downward direction, and here it will be in the upward direction. Okay, because like it is the same conductor only, this should be changed, this should be in the, sorry, this should be changed, right? Sorry, this is not in the same direction, this should be changed. If I have a conductor, two conductors which carry equal and opposite currents, okay, which carry equal and opposite currents, then what will happen, the resultant field will be like this, because it is in the anti-clockwise direction, and here the resultant field will be like this, right, because it is in the clockwise direction. Now what will happen, basically the field winding will try to push this conductor upwards, and it will try to pull this conductor downwards, because the resultant field is supposed to be like this, right? Resultant field is supposed to be like this. So this time I am providing the excitation, as I am providing the excitation, and the output I am getting a force. So there will be force here on the left hand side in the upward direction, and there will be force in the right hand side on the downward direction, which will be equal and opposite, because they carry same amount of currents, right? So it is just like a torque. So a torque will be generated. Torque, when does a torque gets generated? Torque gets generated, torque gets generated whenever whenever there is force in force equal in magnitude magnitude and opposite in direction. So basically this is how the torque gets established in a motor. Now you might have a doubt, sir, how is the current equal and opposite? So what we do is, this is the same coil. So we have a coil, that is, like, we will discuss about this coil as well, that is somewhat like this, and this coil has two ends. From one end I current will be incoming, from the other end I current will be outgoing. It will be connected to a supply, right? So it is a one turn coil, single turn coil or single turn coil. So in a single turn coil, this is the direction of the current, same current goes in, same current goes out. So here one of the side is present of the coil and the other side is present on the other end, so that we are able to produce equal and opposite force. So this is just acting as a motor. We are providing current as the input or power as an input, electrical power, and we are getting this movement, right? So this is a motor, this is acting as a motor, right? Because in motor what happens, we provide the supply and we get the rotation as the output, right? Motor, whatever motor you guys use in various purposes. So if I see that in case of a motor, I am observing this is following just the Fleming's left hand rule. Okay, in case of motor we are following Fleming's left hand rule. What does Fleming's left hand rule says? Fleming's left hand rule says, this we have studied in class 11, right? So if I have a magnetic field in this direction, in the right hand side, and the current is in this direction, then the force will be top. Okay, so this is the direction of the current. So direction of the current is incoming towards me, and this middle, like this is the middle finger will be the direction of current, forefinger will be the direction of the magnetic field, then force will be the thumb, right? Middle finger is the direction of the current, your forefinger is the direction of the magnetic field, and the thumb is the direction of the force. So I can directly see that what is the force. So I also used to remember this thing, that I used to forgot that which one is the middle finger. So always remember, middle finger is the most powerful finger. Why? It has a very special sign. Okay, you guys know what does a middle finger means. So middle finger is the most powerful one. So middle finger, if middle finger is most powerful, so what will I assign middle finger to? Middle finger will be the current. So I also tend to forget this. Middle finger is the most powerful one. So middle finger is powerful. It's powerful. That means it will be assigned with current. Then we see that there is thumb and the forefinger. So forefinger, you have to remember that forefinger is always for the magnetic field. So your forefinger is always for magnetic field. Direction. So these are all direction, right? Direction of current, direction of magnetic field, and your, now only one finger is left, right? Thumb. So if thumb is left, it is basically the direction of the thumb is left, it is basically the direction of the what do you call the force, right? It will be direction of the force. So that's how we understand that we will use Fleming's left hand rule for motor, and whenever there is generator we will use Fleming's right hand rule. So this you have to remember, right? This you have to remember. Okay, so I hope this portion is clear to you guys. So whatever we have discussed is the same written over here. So a salient pole, so this, right, is known as a salient pole, just a name, salient pole. Salient pole, stator, and a single conductor on a cylindrical rotor. When current flows through the conductor placed in a magnetic field produced by field winding, experiences force due to Lorentz force principle. This you study in class 11, so I am not explaining it over here. The direction of this force can be determined by the Fleming's left hand rule. Okay, thumb will be the force, forefinger will be the direction of the magnetic field, middle finger will be the direction of the current. Okay, this force acting on conductors on opposite sides of the rotor results in a pair of equal and opposite forces, thereby producing a torque. This is called electromagnetic torque, due to which the rotor rotates, or interacting torque. Okay, very basic things, this you already know. Now, what is magnetic torque? This torque arises from interaction between the magnetic fields of the stator and the rotor. Both stator and rotor winding should carry current. If one of them does not carry current, then there will not be any torque, there will not be any force, which generate their own magnetic fields, effectively making each behave like a magnet. Okay, so each of them effectively are behaving like a magnet. If you see here, this right is just like a north and south. This will be the north pole and this will be the south pole. So I know, like, if you assume this to be the north pole and this to be the south pole, then what will happen? This will repel, because we know like charges repel each other, like pole faces repel each other. So north will repel north, north will attract south. So south will be coming here and north will be coming here. So there will be a clockwise rotation like this. Okay, I hope you understand. There will be a clockwise rotation. So more conductors will be there. This will be again south, north, something like that. So it will keep on rotating in the clockwise direction. So this time the direction of rotation is in the clockwise direction. So like another way to understand, I'm just saying you how we can understand it differently. So either you can draw the conductors, or you can directly write this as the north pole, this as the south pole, because it is again same conductor only. Okay, so direction of rotation here is in the clockwise direction. So direction of rotation is in clockwise direction. Okay, in this case, so this was the electromagnetic torque. When these magnetic fields interact, they create a net force, due to which there is an attraction and repulsion across the poles, and due to which there is a rotation. Okay, so torque is produced whenever there are two magnetic fields which interact with each other if they have some phase angle between them. Okay, typically they will be sinusoidally distributed. We will discuss how they are sinusoidally distributed in this case, even though I am providing a DC current in the field. We will discuss about that. Okay, so this I have already told you that torque due to rotor current with unexcited stator. So with excited stator and there is no rotor current, then there will not be any torque. But if I have an unexcited stator, if only the rotor winding carries current, it produces a magnetic field. However, no torque is generated in this condition, as there is no stator magnetic field to interact. This is similar to having a current carrying wire in free space. No external field means no force. So just like this, that if I have, let's say, if I don't have this, like this will be the second case actually. This will, let me just, yeah, let me do this. If I have a single current carrying wire, if I have a single, like this is just the case where the stator is unexcited, only the rotor is excited. So let's assume this has a rotor, right? So it will produce a magnetic field like this. This we know from our basic 11, 12, right? It will produce, like, what will be the direction of the magnetic field? Thumb is the direction of the current, and the fingers, culling of fingers, are the direction of the magnetic field. So will any force be present here? No, right? This current carrying wire will not experience any force. But now if I do something else, if I place another current carrying wire near it, right? If I place another current carrying wire near it, right? This will be the direction of the magnetic field. Very bad drawing. Okay, this will be the direction of the magnetic field. If this is the direction of the magnetic field, what can I say? Again, this current carrying wire will experience a force. What is the force? I1 into I2 divided by distance between them. I hope you remember, right? So here the force is proportional to I1 into I2 divided by the distance, and I know I1 and I2 is directly proportional to the magnetic fields. Okay, so that's why they experience a force. Okay, this I hope you know already. So just giving you a brief idea, right? So I hope it is clear that how does a torque get generated in a DC machine. Very important to understand how does a torque get generated. So torque will be proportional to the mmf of the stator. Stator mmf, like magnetic field, is proportional to the mmf only, because I know my flux is mmf upon reluctance, and my flux is proportional to the flux density. So I can write this as stator mmf stator mmf, then I can write this as rotor mmf, and I can write this as like and the angle between them, sign of angle between them. Why does this sign come up? I will explain that with the EMFT lecture. So EMFT I have already covered. I will explain that with EMFT. Okay. Now few things, few assumptions we need to make while doing this kind of torque analysis. What kind of assumptions I have made? That permeability of the stator and rotor are infinite, because I want the flux to be same throughout, but it will not be infinity, right? There will be some reluctance. So the magnetic field will keep on changing at different positions. There is no magnetic saturation. There will be ideally, practically there will be magnetic saturation. Air gap is uniform and much smaller than the machine radius. If I don't assume the air gap to be uniform, right, again the reluctance will change. If I don't assume this air gap to be uniform, the reluctance will change. If the reluctance changes, the magnetic field values also will keep on changing. Okay, so magnetic fields are sinusoidally distributed. This we will discuss later on. And magnetic field is normal or tangential component. So magnetic field is always normal to the conductor, no tangential component is there. Okay, because if I have a current carrying conductor like this, and if the magnetic field is also in the same direction, right, actually it is not cutting. So the magnetic field, the flux must cut the conductor for a force to get generated, right? I hope we remember this point. Flux, the amount of flux cutting the conductor, due to that a induced EMF is generated, right, according to Lenz's law. So if both are parallel to each other, then there will not be any force generated. So this is from where the sine theta angle comes. So here what is the theta? Here the theta is 0 or delta is 0. So delta is 0, that means sine delta is 0. So that means there will not be any force generated. If my, let's say, current was in this direction and the magnetic field was perpendicular, so it is totally cutting the current carrying conductor. So here the theta is 90, so here the force will be maximum, because this magnetic field will try to pull it in the direction of the force, right? So here the angle theta is 90, so sine 90 is 1, so here it is maximum. So that's why there will be some force here and there will not be any force here. Okay, I hope you have understood this basic point. Now let's understand how the magnetic field is actually sinusoidally distributed. How is it actually sinusoidally distributed? That we will discuss now. So if I see, just talking about this field flux, now I am not talking about the conductor anymore, I am just talking about the field magnetic field, because this will mostly be dominating. The field magnetic field will mostly be dominating, right? The magnet, I am currently ignoring the magnetic field due to the conductor, right? Currently I am ignoring the magnetic field due to the conductor. I am just discussing about the magnetic field due to the fields. So ignoring magnetic field due to conductor. So if I ignore it, if I just see this conductor in isolation, let's see this conductor in isolation. If this conductor is here, will any magnetic field cross through it? No, right? I see there is no magnetic field. So at point A, the magnetic field is 0, right? And there are multiple conductors here. So again it will, what, all these conductors are present, I am not drawing all of them. They will experience some force in the clockwise direction, so they will rotate in the clockwise direction. So at some point at t equal to 0 or omega t equal to 0, here the flux is 0. The flux is 0, that's why the B is 0 here. Now as this conductor is rotating, it will reach to point B, and here the flux will be maximum. Why? Because it is the closest to the field, right? Closest to the pole. So here the flux density will be the highest, because most of the flux lines are cutting through here, right? So here the flux density will be the highest. And remember, this is conductor, this is just the just the side view of the armature. Armature is something like this, right? So you might have a doubt, sir, how the direction of the current and the direction of the magnetic field are perpendicular to each other. So armature actually is just a long cylindrical object. It is not a spherical object. Okay, so this is the armature basically. So in armature the currents are like this. Currents are like this. This is the wire and this is the current, right? And magnetic field is like this. So that's why the magnetic field is always 90 degree. It will always be 90 degree, right? This is the 3D view. Okay, this is the armature. So it will experience a force in the clockwise direction. So if it experiences a force in the clockwise direction at omega t, let's assume that omega t equals to pi by 2, it reaches to point B. And I see it is maximum. It will be maximum here because most of the flux lines are passing through here, right? Again, after a certain point of time, it will reach here. Again, the flux line will be lower, right? Minimum, because no flux lines are passing through here. Again, the conductor will reach here at point D. Here again the flux lines will be maximum, but this time something will be different. Direction of flux lines will change. It will be in the negative direction. Why? Because here the flux lines was incoming, here the flux lines are outgoing from the conductor, right? That's why it will just be in the negative direction. Magnitude will be same, just the direction of the flux lines will be in the negative direction. So basically, roughly what I can say, that at position B, I can write at position B, point B, my conductor is here. This is my conductor, right? This is my conductor that is present over here, and the flux lines are like this. Flux lines are like this, right? So here my magnetic field density will be maximum plus Bm. Okay. Then my when I am at point D, when I am at point D, right? At point D, point D, the like magnetic field density is going outward from the flux, right? Okay. So conductor is experiencing different magnetic fields at different positions. If I see, the magnitude of the flux changes with time, but axis of the flux remains same. I mean, this flux is constant, but as the conductor is rotating, then the magnitude is changing, right? If it was stationary, then there would not have been problem. It would have been simple single magnetic field only, constant magnetic field only. But as I am moving, the magnetic field direction is changing. Magnetic field value is also changing, right? So it is going from plus Bm to minus Bm. So it is somewhat like a sinusoidal, because here if as soon as it will come near periphery of the magnetic fields, the flux lines will increase. Again, more nearer, flux lines will increase further. Again, most nearest, the flux lines will be maximum. Here again the flux lines will reduce. Again it will go negative here because it is leaving. Again negative. Again it will become 0 here. Again it will increase, like this. It will keep on happening. It will increase, decrease as the rotor rotates. Okay. So if the field coil is excited by a DC current, the conductor experiences a magnetic field, right? That is sinusoidal. Conductor experiences a magnetic field that is sinusoidal. That is the key point or important point to note here, right? Very important point. This is the conductor basically. This is the armature basically. Okay, I hope you have understood this basic point, right? So few important points I want to write here, that the conductor experiences different magnetic flux density at different positions. So key points, what are the key points? First key points, right? Key point is that the conductor if I rotate, now I am rotating, the field coil is excited and I myself am rotating. I myself am rotating this armature. This time I am rotating the armature because currently the conductor does not have any current. So I forgot to mention this. So here, right, I am rotating the armature. I am rotating the armature. Okay. So if I am rotating the armature, no current. Current is zero. No rotor excitation. I'm not providing any rotor excitation. That's why I am ignoring the magnetic field due to conductor, because I have not provided any rotor excitation. I have not provided any rotor excitation. That's why the magnetic field due to the conductor is zero, because I is zero. IA, armature current is zero. That's why I forgot to mention this. I'm really sorry. I forgot to mention this. Okay. Okay. So now if I don't provide any excitation and I myself rotate the armature, then the conductor experiences, first point is conductor experiences different magnetic field at different points. Okay, the first point. What about the second point? Second point is here important point to note. Even though the field coil is excited, even though the field coil is excited by DC current, the armature is experiencing a sinusoidal magnetic field. Okay, very important point. Like the armature will experience a sinusoidal magnetic field. Okay, so if this conductor is experiencing a sinusoidal magnetic field, that means the field flux is changing. Flux is changing across the conductor. If the flux is changing across the conductor, what I can say, an EMF will be induced. So I can directly comment that an EMF will be induced. We will try to derive the expression of the EMF. Okay, so what I know, if flux across the conductor is changing, this time I am not providing any excitation, I am just rotating the conductor. I myself am rotating the conductor. So if flux is changing the conductor, if flux is changing across the conductor, that means what? That means an EMF will be induced according to Lenz's law. E will be equals to n d phi by dt, right? If you remember, it was n d phi by dt. I'm just talking about the magnitude for now. I'm just discussing about the magnitude. Okay, so if let's say for a single conductor, if I have n is the number of turns, if it's a single conductor where n is 1, right? For a single conductor, I want to find out the expression for a single conductor, how much EMF will be induced if I keep on rotating my armature. So E induced will be d phi by dt. I'm just discussing about the magnitude for now, discussing about the magnitude, not discussing about the sign. Lenz's law, I know it will oppose it, we will write the sign later on. So what is the flux basically cut? How much is the amount of flux cut here? So the flux will always be like current is going in this direction, right? Current will be for the conductor, or the conductor current will be in this direction, right? And uh, so what is the area that the flux cuts? So flux will be in this direction, right? I have already given you the 3D figure. Flux will be in this direction, current is in this direction. So let's assume current to be in this direction and flux to be in this direction, right? This will be the direction of the flux. So I have a cylindrical wire like this, right? And the flux is 90 degree always cutting. So if from the in front, what I will see, I will just see a square box like this, right? Rectangle, square rectangle like this. That flux is coming out here. Flux is cutting this rectangle, right? So what is the area? Because I know the magnetic field density, I don't know the flux, right? So for finding out flux, what is flux? Flux phi equals to B into area, right? So I observe that here the area vector is in the same direction only. And what is the area? Area is this length basically, this length, and it is the this height x, small dx, because I just want to calculate the EMF induced in a very small portion of the armature. I'm not covering the whole portion, just very small portion of the armature, right? So it will be basically yeah, dx yeah, delta x, right? Small x, that is delta L into delta x. So this area will, this is delta x, small area delta x. So this will be L into delta x. This will be the small area delta A, right? So my small flux magnetic field is constant B, not constant, sorry, it is a function of time, B into L delta x. That is what my delta phi is. So this I can write as delta phi upon delta t. So delta phi will be B into L into delta x upon delta t. And what is delta x upon delta t? Distance, change in distance upon change in time. That is basically velocity. So from here, very famous formula comes up, BLV. And as here the angle between the this current direction and the flux was always 90 degree, this was simply BLV. But actually, if there is some angle between the current and the flux, the value will be BLV sine theta. BLV sine theta, that's it. Okay, that's the most simple derivation. This you have already studied in class 11, 12, right? Same thing is written over here. It is BLV, and as it is always perpendicular, it will be BLV sine theta. Same thing I have proved in my AMFT classes as well. If you want to go more deeper into this like concept, how is it BLV? Go into the magnetostatic, I mean electromagnetic induction. There I have derived everything, every single thing. You can go through this, you can read through this. Ultimately, the expression of the motional, this is also known as the motional EMF, comes out to be BLV sine theta. Okay, you can go through those lectures. Of course, we don't have time to cover everything up. So this is the magnitude of the motional EMF. B cross V, LA sin theta. Sin theta will not be there if it is B cross V, right? B cross V automatically gives sin theta. So now I hope you have understood the basic principle of motor and the basic principle of generator. So in case of generator, if I am rotating this in the clockwise direction, what will be the direction of the current now? What will be the direction of the current? That is also very important fact to note here. So the direction of the current will be given by the Fleming's right hand rule. For a generator, the direction of the current will be given by the Fleming's right hand rule. So I will write here direction current will be This will be the direction of current basically. So in this case, let's see in this case what will happen. So if I just take this case, right, I know the direction of the field. So in case of Fleming's right hand rule, I'll just use my right hand rule. All the fingers notation will be same only. So the direction of rotation is in the right hand side, right? It is rotating in the right hand side direction, right? So the force will again be along the thumb. The field is the forefinger. Forefinger is along this direction, right? So it is rotating in the right hand side and the field is in this direction. How will I? Okay, it is rotating. Okay, sorry, it is. Oh, sorry. If my conductor is somewhere here, if my conductor is, let's say, somewhere here, not here, if let's say here it is, because here there is no magnetic field, right? Here only there is magnetic field. So here what is the direction of the rotation? It is in the top, right? Here the direction of the rotation is in the top, right? So thumb will be in the top. Again the magnetic field is on the right hand side, so my current will be coming towards me. So here the current will be, sorry, this is the left hand, right? So I have to use the right hand, so my right hand will be broken. So basically the thumb will give me the direction of the direction of the this force, and the forefinger will give me the direction of the magnetic field. And if you just see, I am curling my fingers here. So basically how will I do this? This thumb will give me the direction of the force. Okay, and yeah, so the middle finger is going inwards, right? So if the middle finger is going inwards, that means what? That means it is basically cross. So if you observe, the direction will be just opposite. For a motor, if you remember, when the direction here was dot, then it was rotating in the clockwise direction. And for a generator, if I am rotating the machine in the clockwise direction, then the current direction changes. So just opposite of the motor. So it will be always, it will be just opposite of the motor, right? Use Fleming's right hand rule. Use Fleming's right hand rule. So just opposite of motor. Okay, so just one key point I wanted you to have an idea on, right? So this will not change. Just I will use the right hand, but this notations will not change, right? This notations will be same. Yeah, this thing will not change. This thing will be same. Okay, keep this in mind. Where am I? Here. Okay, so these are the things, basics that you need to get clear, right? These are the basic things that you need to get clear. Now we have already discussed, this is my flux density waveform, right? So there is very important relationship. What is this omega t? What is this omega t? Remember, this omega t is with respect to electrical quantity. How I will explain. So currently if I have two poles, right, only north and south pole, two poles. For two poles, this is my flux direction, and for two poles, if I rotate a full clockwise, full 360, this will be the full 360, right? If I am at position H at omega t equal to 0, then I will go into then I go to position B where the flux density is maximum. So let's say initially I was at position H, right? Initially I was at position H. Okay, so what is the mechanical displacement here? Initially the mechanical displacement is 0 degree. So like theta mechanical, theta m equal to 0 degree, and the flux also is here 0 only. So theta electrical quantity is also 0. So if I move here, right, if I rotate 90 degrees, if I rotate here 90 degrees, so if I rotate here 90 degrees, that means how much have I moved physically? Physically also I have moved 90 degrees only, and in the electrical domain, how much have I moved? In the electrical domain also I have moved 90 degrees, because here at this point B, the flux density is maximum in the positive direction. That means omega t is pi by 2, because the reluctance here is minimum, so most of the flux lines will pass through here, right? So theta E also is 90 degrees. This I am discussing when my number of poles are 2. I have a north pole and a south pole, right? Now again, if I reach point D, physically I have moved 180 and the value is also 0, right? So again, if I move point A, physically I have moved 270 and the value is also negative. Again, if I move back a whole 360, the magnetic field, magnetic flux density also will be 0. The physical movement also will be 360 degrees. So this is fine. Here the mechanical and electrical degree is same. Now let's come to the case where they might be different in this case. So if I am in this case, right, things will be a bit different here. Why? Because again, if I just assume this to be my north pole, like these are my windings, this to be my north pole, south pole, this will be again a south pole, and sorry, this will be north pole, south pole, sorry, this will be north pole, south pole, north pole, south pole, alternating poles. Okay, generally we connect alternating poles like this. These are the connections of poles, right? Alternating poles. This will be north, south, this will be north, south. So magnetic field will go from here and then magnetic field will go from here. That's it. Here, here, here. So what will happen is that if I have 4 poles now, so now the number of poles is 4. If the number of poles is 4, let's assume initial position is here, somewhere H, right? If I move, let's say this is 45 degrees. If I move 45 degrees, initially is the magnetic field here 0? Now here, right, the magnetic field is not 0 anymore, because some magnetic field is there, right? Something is going in here. So from north to south there will always be a magnetic field. So here the magnetic field is not 0. So where is 0 actually? So somewhere here the magnetic field is 0. Somewhere here the magnetic field is 0, because like very low amount of magnetic field will pass through here. So I am assuming this point A to be the point where the magnetic field is 0. That is my assumption. So how are the direction of the magnetic field made? So you can assume it like this. So direction of the magnetic field, I can draw it like this. This will be the direction of the magnetic field. North pole magnetic field will come here and go here. North pole magnetic field will come here and go here. Again, north pole magnetic field will come here and go here. So I can draw with different color actually. And same here as well, the north pole magnetic field will come here and go here, and north pole magnetic field will come here and go here. Okay, so what I observe is at this point A is right, it is not minimum anymore, but at point A there is no field lines passing. So field lines will come here and go there, right? There is no field lines. So my starting point will be A. So at point A my magnetic field is 0 and my theta m is 0. Okay, and as magnetic field is 0, as it is sinusoidally varying, so my theta e also will be 0 only, no problem. But let's see at what happens at different points. This is at point A. Let me see at point B. So at point B, if I reach at point B, what will happen at point B? So at point B, physically how much have I rotated? Physically I have rotated 45 degrees, correct? And what is the magnetic flux density here? It is maximum, right? Most of the flux lines are passing through here. So magnetic flux density is maximum. So electrically the angle is actually pi by 2, because when is sinusoidal function maximum? Either pi by 2 or 3 pi by 2. So it will be electrically, here the Bm, sorry, not the B, sorry, B will be 0. Here the B will be equals to plus Bm. So previously I have written Bm, no, I have not written. So B will be equals to plus Bm. So if B is equals to plus Bm, so my theta m, physically how much have I rotated? Physically I have rotated from this position A to this is 45 degrees, right? So this is 45 degrees. But electrically, if I see the flux density waveform, I am at pi by 2. So it is, electrical angle is pi by 2. So there is difference between electrical and mechanical angle. Physically and electrical quantities, there is bit of difference. So electrically the flux density has moved up by 90 degrees, but physically I have moved only 45 degrees. Let's discuss about other cases. Now if I am at point C, again at point C, physically I have rotated a whole of, from this point to this point, I have rotated a whole of 90 degrees. So this portion is 45 degrees. So I have rotated a whole of 90 degrees, right? So if I have rotated a whole of 90 degrees, That means that the here what is the flux or the flux density? 0. No flux lines are crossing through here. So flux density is 0. Physically how much have I moved? 90 degrees. Flux density is 0, that means I am at point C. So this is the point where my theta is 180 degrees. So at C my magnetic flux density is 0, my theta m is 90 because I have rotated physically 90 degrees, and theta e is actually 180. So I will just do the last one. Let's do this one. So if I am at here at point D, if I see how much have I rotated? I have rotated a total of 135 degrees, right? This is 45, this is 45, this is 45. So mechanically I have rotated a total of 135 degrees, but electrically where am I at? Electrically again it is peak, but this time the flux lines are going in the opposite direction. It is coming out of the, going out of the conductor, right? Going out of the conductor, not incoming to the conductor, going out of the conductor. So if it is going out of the conductor, what does it mean? What does it mean if it is going out of the conductor? It is negative. It is negative. So here my flux density will be minus, it will be peak because most of the flux lines are passing, but it will be negative here. It will be minus Bm. Okay. Okay. So this theta e is equals to what? How much is the electrical angle? Negative in the opposite direction. That means it is in the 270 degrees, right? So I can right now identify a relation. What is the relation? Relation is my theta electrical will be 2 times theta mechanical. So I am observing that as I am changing my number of poles, the theta electrical and theta mechanical are changing. So what is the simple relationship? The simple relationship is that my theta electrical will always be equals to p by 2 of theta mechanical. This is the most basic relationship, right, between the electrical and the mechanical quantities. So one more thing I can write that about the speed. So if I am rotating 180 degrees in the mechanical domain physically, then electrically I will rotate more because I am passing through more poles. If I am passing through more poles, the cycles will change faster. The cycles will change faster. Now one more relationship I can use. What is the other relationship? That I know theta electrical is equals to p by 2 of theta mechanical. Okay. So I know theta electrical is equals to p by 2 of theta mechanical. Now p by 2 is just a constant number if I differentiate on both sides. So if I differentiate on both sides with respect to time, so this will be theta e d theta e by dt equals to p by 2 d theta m by dt. Okay. So what is d theta e by dt? It is basically omega e. Omega e. What is omega e? Omega e is basically the frequency. I will write the frequency term as well. Omega e electrical speed is equals to p by 2. P by 2 is just a constant, equals to the omega m, that is a mechanical speed. So electrically how fast my waveform is changing is p by 2 times the mechanical, how fast your rotor will rotate, right? Now this can be further rewritten, right? How can I further rewrite this thing? So what is omega e? Omega e is basically 2 pi f, the frequency, right? Frequency of the waveform, frequency of the flux density, 2 pi f, and it is p by 2 of 2 pi n. What is n? N is the rotations per second or revolutions per second, right? N is the revolutions per second. So f will be equals to p by 2. So electrical quantity, electrical frequency will be p by 2 into n, the mechanical quantity. It will be equals to p by 2 into n. So this is mechanical. So n is rotations per second, right? N is rotations per second, not rotation, or revolutions per second, revolution per second. We can convert one more thing. We have capital N. What is capital N? So small n can be written as 2 pi n by 60. Is it correct? Or no, sorry, not 2 pi n by 60. Small n can be written as n by 60. What is n by 60? So n by 60 is the revolutions per minute. Instead of writing in seconds, we generally write in minute. So this is a standard notation that we follow. So here my N is revolutions per minute. Instead of second, I'm just converting this into minute, right? So my equation F will be equals to P by 2 into N by 60. This is a very, very famous equation. This further you can write my N equals to 120 F by P. This will be used in your induction machines, in synchronous machines as well. This is a very, very important relationship that you know, right? That I know you have mugged up, but today I have proved it how it came. Okay, I have proved it in front of you how it came. So these are the equations basically. So number of EMF cycles generated electrically is P by 2. In P by 2 cycles, my rotor will rotate a complete revolution. Okay, that is what this equation signifies. Okay, so electrical speed, the key insight here is electrical speed is a multiple of mechanical speed, and the multiplying factor is half the number of poles. Okay, that is the important point that we want to discuss here. Okay, so one more term is there named as pole pitch. What do we mean by pole pitch? So pole pitch, right? I will copy this. I'll copy this diagram. Pole pitch is what? Pole pitch is the angular distance between two centers of adjacent pole. So mechanically, here what is the pole pitch? Mechanically, pole pitch is 90, right? They're separated by 90 degrees. So, but always remember, pole pitch will always be 180 degree electrically. Why? Because if a conductor is here in the north pole, it will experience plus Bm amount of magnetic flux. If the conductor moves here, right, in the south pole, it will experience minus Bm because the direction will get changed. That's it. That's it. So always there will be a phase shift of 180 degree between the pole, two adjacent poles, electrically. In electrical terms, this will always be valid, but mechanically this will keep on changing depending on the number of poles. So here in this case, here the pole pitch, right? Pole pitch is 180 degree electrical or 90 degree mechanical. 90 degree mechanical. Okay, remember this, either it is 180 degree electrical or 90 degree mechanical. So by default, if nothing is mentioned about the angle, it will be electrical angle. Okay, if you want to mention it in mechanical angle, you have to write mechanical. Right? So same example, if it is a 4-pole machine, so one mechanical revolution will be 360, but electrical angle will change, right? Here it will go from plus Bm, minus Bm, plus Bm, minus Bm. So there will be 2 cycles. In one complete physical rotation, there will be 2 cycles, right? That's it basically. So now let's discuss about the wave shape of your flux, right? To be honest, we don't actually want pure sinusoidal wave shape, right? Because we are anyways making DC. We don't want pure sinusoidal. Why? Because when we will make this, when we will rectify this, right, the rectified waveform will be somewhat like this. Okay, I will show you how we are rectifying it, but just giving you a brief that when we are rectifying this waveform, omega t, and this is b, so it will be pulsating like this, and there will be ripples here. So what we do is, instead of making it purely sinusoidal, we make it flat topped. What is the reason for making it flat topped? We make it flat topped so that what happens is that basically, if I now rectify this, right, if I rectify this, the waveform will be somewhat like this. So it has less ripples. It has less ripples, right? So my waveform has less amount of ripples. So that is the advantage, right? I want less ripples. Why? Because I want pure DC. I want my output to be pure DC. So this will have less ripples, right? This will have more ripples because like the peak value is very small and it will have more ripples. This is pulsating less, like it is remaining at this value for longer amount of time. So how do I make it? Why was this coming in the first place? If you remember, here the flux density was maximum. Why? Because MMF is constant. What is the MMF provided by this field? it is constant, n into if, right? That is the nf into if, right? Divided by reluctance is the flux basically, right? This is the formula for flux. So here, right, if the conductor is here, the length between this field pole is the lowest. Here the gap, air gap is the lowest, correct? Here the air gap is the lowest. Here, if my conductor is here, the air gap is again increasing, right? Air gap is increasing. So this G2 and G1 is here. So G1 is less than G2. So if the air gap reduces, the reluctance also reduces. So the flux density increases. So here the value of flux density will be peak. That's why I am getting a peak over here, right? But what if I keep this air gap constant? So here it is not G1, G2. This air gap I have kept it constant. How? By chamfering the poles. So this G1, G2, this air gap across the field lines is always constant. Outside the field it is again changing. Does not matter. Here it is changing. Totally fine by us. But inside this north to south it is always constant. So my G1 is equals to G2 is equals to G3, right? Air gap is always constant. So we make it constant to get to this form, right? To make our flux lines flat top so that there is less ripples, so that I get more closer towards DC, more DC. So that is the sole reason why I want to do this, okay? That is the basic sole reason, because I want to make the flux density here uniform. So that MMF is anyways constant, just the reluctance is not constant. So here the flux density is uniform because the air gap is not changing. Flux density is uniform. Okay. So with commutator, what happens here? I get the I will explain how do I get this commutator to waveform, right? I will explain this. Don't worry. So here, what is the actually? Remember, your induced EMF is actually not pure DC. It is pulsating. So in this case, if my flux is purely sinusoidal, what will be the average? So this we already have studied in AC analysis of network theory. V average will be 2 Vm, or 2, like this is 2 into Bm, right? Bm. So Bm will be proportional to Vm only. So VO average will be 2 Vm by pi. Okay, or my B average will be 2 Bm by pi. That is the average of a fully rectified waveform. Okay, so what is this value? What is this value basically? So what I can say is my, like, how do I find out this value? So my flux, right? My flux is actually sinusoidal flux, right? So I want to derive the expression for the average output voltage. How do I find out the average output voltage? So in this case, my flux is sinusoidal. So if my flux is sinusoidal, B is some Bm sine omega t, correct? Now how do I find out the, or my flux also will be some phi m, sine omega t per pole flux, right? Per pole flux. This is the per pole flux. Okay. So what will be the induced voltage? V equals to n d phi. Induced EMF is n d phi dt. I want to prove something here. So voltage is n d phi dt. So induced voltage. So it will be equals to, what is phi? Phi is some phi m per pole flux, right? So it will be n into d phi dt. So it will be phi mp p into omega. Omega, I remember, is in electrical, right? It is electrical, into cos of omega t. So roughly what I can comment is my voltage, induced voltage, is also proportional to the number of turns. So my number of turns, right? N is the number of turns, which in turn is proportional to the number of conductors, right? Number of turns, which in turn N is proportional to the Z. What is Z? Z is the number of conductors. I will derive this expression later on as well. Number of conductors. And my omega is just the speed. Omega is also, I can write omega is also proportional to speed, because it is electrical here. Omega is electrical, but I can write it also proportional to the speed of the rotor, because they are just like, what is omega electrical? Omega electrical is P by 2 of omega mechanical, right? So that's why I can directly say it is just proportional to speed of rotor. So my induced voltage is proportional to the speed of the rotation. Okay, speed in RPM also you can write speed into the flux per pole. It is proportional to the flux per pole, and it is proportional to the number of conductors. So don't worry, I will derive this expression exact value later on, but for now just I want you to get an intuitive idea how that formula comes up, right? Before deriving that expression, I want you to get an intuitive idea. So my voltage, induced voltage, will be proportional to the speed, flux per pole, and number of conductors. And how are we actually making it like DC, pulsating DC? I will just describe it now. So everything, right, in one first lecture I am giving you a teaser basically of what will happen in the DC machine. I'm trying to explain everything in the first lecture. So of course in the next lecture we will derive the things. Now few students might have a doubt, sir, here there are more harmonics than here, right? It is purely sinusoidal, here there are more harmonics. But is it a problem? So here, right, harmonics will be more harmonics. Is it really problem? Do I really care about harmonics right now? When did we care about harmonics? We cared about harmonics when we wanted our output to be purely sinusoidal. But do I want my output to be purely sinusoidal? No, I don't want my output to be purely sinusoidal. I don't want my output to be purely sinusoidal. I want my output to be DC. So no problem, right? Because I want no problem. I want my output to be purely DC. There is no problem with this. I want my output to be purely DC. Why? Because I want better average. So this will give me less pulsating, right? This will be less pulsating. Okay. So yeah, that is the case. Now let's discuss how does commutation works. Okay. Although we will learn this later on when we will discuss about the construction. Just wanted to give you a bit of idea how does commutation works. So commutation is just a mechanical part. So this is the commutator basically, and these are my this is my conductor coil, and this is the commutator. Okay. So let's say there are two fields, north and south, right? This north and south. So initially this is the direction of current in the north pole, and this is the direction of current in the south pole. Okay. When my commutator is in this position, first case, right? Case A. So current is like this. It will come out of this brush, then of course it will come like this, right? This will be the direction of the current. Okay. Now in the case 2, what is happening here? There is no magnetic field. If there is no magnetic field, the current will almost be zero, right? Current will almost be zero here. Now in the case 3, if you see, in the case 3, this is the LK section. So previously in the LK section, the current was like this, right? In the case A. In the case A, here in the LK section current is zero because the magnetic field is like this and conductor is here, so no magnetic field is present. So current will be zero here, right? Current will be zero. Although they are showing it, current is actually, the value of the current is zero here. Now let's come to the case D. In the case D, my LK is on the right hand side now, and of course according to the magnetic field, I will use my Fleming's right hand rule. If I use my Fleming's right hand rule, the direction of the current you will get just in the opposite. This we have already discussed. So direction of the current will be in this. Now you will say, sir, then how commutation is happening? Sir, how commutation is happening? You are having the doubt how commutation is happening. So basically the important portion is, although the conductor is carrying a alternating current, right? Conductor is carrying a alternating current, but in the brushes the direction of the current does not change because there is a mechanical gap here. So if we observe in the case A, the current direction was like this from this brush. It was outgoing from this, let's name this brush B2, B1. So in the case A, the current was like this, it was outgoing. In the case D as well, although the conductors have changed, but current is still outgoing from brush B2, right? and still it is incoming in the brush B1. So outside of this brush, whatever load I am connecting, that is only observing that it is a DC, it is a pulsating DC current. But inside the conductors, individual conductors are changing the current direction. Okay, this is the crux, right? Here I have explained the same thing. Let's say I have a field ABCD, segment segment ABCD, right? If I have a segment ABCD, first in the AB segment, if this is the first position, okay, current is like this, outgoing from brush B1 and incoming to brush B2, right? In the second case, the current is outgoing from brush B1 and it is again same, because remember the segments has changed, right? So now this AB segment, because there is a mechanical gap, this AB segment, okay, sorry, this is a bit wrong. Okay, sorry, this will not be like this, because there is a mechanical gap. I'm just done a mistake here. Yeah, this will not be like this. Now this because remember here there is a mechanical gap, right? So mechanically this coil is just, it is just touching here. So how is it connected? So this is my slip ring and this is just a wire or a rod. A rod is just touching here the brush, right? So the rod is just moving, brush is stationary, rod is just moving here, and there is the other brush, right? So other brush is here. So rod will come from brush B1 to B2. Okay, very bad drawing, but a rod will come from brush B1 to B2. Okay, brush B1 to B2. So here what is happening, although the direction of the current across the coil will change, right? Because initially it was going from bottom to top, now it will be bottom to down. Why? Because the field, the direction of field has changed, right? So direction of field is, now it is outgoing, previously it was incoming here, so now it will be outgoing, right? So hence across the conductor, this is the portion of the conductor AB, the direction has changed, but ultimately in the brush B2 this direction will be same, still current is incoming to brush B2, outgoing from brush B1. Same thing is happening over here, right? Incoming to brush B2, outgoing to brush B1. So that is the advantage of commutators. So don't worry, we will discuss about commutators more, but just I wanted to give you a teaser, that's it. Okay, if I don't use this commutator, right, the current will just be alternating across the output. If the load I connect without commutator, if I connect the load, the current will just be alternating. Okay, so same thing, whatever I have discussed is written over here. So what are the key points till now? What we have learned? We learned about electrical angle, we learned about frequency, electrical frequency, and the mechanical speed. We learned about electrical angular velocity. We learned about pole pitch, it will be always 180 degrees. So and few more things, whatever we have discussed I have written over here. Okay, so one more thing, so what will be the B average also I have forgot to write it. So what will be the B average? So B average will be 2 bm upon pi. So because it is, if it is purely sinusoidal, so this formula is valid if it is purely sinusoidal. Okay, if it is purely sinusoidal, then how it is B average? So I'm talking about the rectified portion, right? I'm talking about the rectified portion, not talking about the alternating portion, right? So if it is pure sinusoidal, then my B average will be this. Now what will be the flux per pole? How do I calculate the flux per pole? So what is flux? Flux is flux density into area, right? So if I have a rotor like this, okay, now this will be only valid for this case, it will not be valid for any other case, right? So if I have a rotor like this, what will be the flux per pole, average flux per pole cutting to the this rotor of length L and diameter, circular cylinder diameter D, right? So flux will cut like this, right? Flux will come something like this. This will be the flux, right? So average flux will be the B average into area. So B average is basically 2 bm by pi. And what is the area that I am observing? In 2D figure, if I see, it is just like a rectangular portion. Okay, just like a rectangular portion cutting. This flux is cutting the rectangular portion, right? So whose length is L. So actually here, right, the flux lines are cutting all over the place. So they are cutting over the, I mean, they are cutting throughout the cylinder, right? So conductors are throughout the circumference of the cylinder. Okay, conductors are there throughout the circumference of the cylinder, here, here, here. So there are flux lines cutting all over the cylinder. So if I just cut this conductor somewhere, okay, then what will happen is, what will be the length if I cut this cylinder, right? If I cut this cylinder from here, the length will be still L, right? What is the breadth? What is the breadth? It is the circumference of the cylinder, right? So it is basically equals to pi d. This will be pi d. So the flux lines are cutting all over the, I mean, like this 3D diagram, right? It is cutting all over the all over the area of this what do you call, the surface area of the cylinder, right? So I can write phi will be equals to 2 bm into area, 2 bm into area. Area is basically pi L into pi d. It is just a rectangular sheet, L into pi d. So sorry, not bm, sorry, it is 2 bm by 2 bm by 2 bm by pi, right? It will be 2 bm by pi. So the average flux per pole, remember this is the formula for average flux per pole for a sinusoidal, flux waveform, right? Flux per pole. So this will be equals to 2 bm L d upon okay, so this will be 2 bm upon LD only. Yeah, this will be 2 bm yeah, LD only. Now this is the average, sorry, one point I missed, this is the flux, right? This is the flux. Now what is the per pole flux? So actually this is the overall flux, right? How much flux is getting contributed by per pole? So if I have p poles, then per pole flux will be just this divided by p, right? I missed this point. This will be this divided by p. That's it. Because this is the overall flux contributed by all the poles. Contributed by all the poles, because this conductor armature will rotate throughout all the poles, right? Here it will rotate throughout all the poles. Where is the 4 pole picture? 4 pole, yeah, here, right? So the conductor will rotate throughout all these poles, and due to that, this is the flux waveform, right? But how much flux is contributed by a single pole? That if I want to find out, I will just simply divide it by pole. Remember, whatever I am deriving here, per pole flux. So this is the per pole flux. Per pole flux. Okay, so this is the per pole flux. So all this whatever we are discussing, it is for pure sine. If my waveform is not pure sine, then this formulas will not be valid. So this formula will be also valid for synchronous machines as well. Okay, do I want you to remember? No, I just want you to remember the derivation, how I derived it. Okay, automatically formula will get remembered, don't worry. Synchronous machine also we will use this formula. Okay, so that was about it. Now let's discuss about the types of DC machine. So we will try to cover today we will try to only cover this separately excited DC machine only. So there are many types of DC machines. DC machines can be classified on how the field winding is energized, as I discussed previously, whether it uses a separate power source or derives excitation from its own armature voltage. So armature also generates a voltage, right? Armature coils. So if I am able to provide the field current using its own armature voltage, then it is known as self-excited. Otherwise, it is known as separately excited. And there is one more kind of DC machine known as permanent DC machine. Now, what have we discussed till now? So we have discussed that our induced voltage. So we will discuss that, like there are many types of DC machines. Today we will discuss about these two only. Okay, in this lecture. So one more thing I have discussed, that my induced voltage is proportional to what I have already derived. Induced voltage is proportional to the flux, right? Per pole flux, right? Per pole flux. Then proportional to the number of conductors. It is proportional to the speed RPM. Also, it is proportional to the number of poles. If the number of poles increases, the overall flux also will increase, right? Here the overall flux will increase, right? Here the overall flux will increase. If the number of poles increases, then the induced EMF also will increase, because there is more magnetic field. So just an intuition, I have not derived the formula yet. I'm just telling you that what is my induced EMF proportional to. My induced EMF is proportional to all these quantities. Now one more thing I want to discuss. Let's first discuss about this permanent magnet DC machine. Permanent magnet DC machine is very easy. Here there is no field winding because a permanent magnet is there, so it will always produce a magnetic field no matter what. So important point here is this V is actually known as the terminal voltage. The voltage that I will be able to see, terminal voltage. And in case of generator, the whatever the induced voltage, it is known as the generated voltage. It is known as the generated voltage. Okay. Now in case of motor, right, in case of motor, the voltage that get induced is known as the back EMF because it opposes the terminal voltage. I will discuss this about this back EMF later on. Don't worry, I will discuss about this. For now, just understand that it is called as back EMF because it opposes its initial cause. Okay, why the name back EMF, that also I will discuss. So this is known as the back EMF. This is for a motor, right? Here it is a permanent magnet, so I don't need to excite the field coils because the field coil is already excited because it is permanent magnet, right? So in a permanent magnet, the phi is constant, it is DC, and no need to excite the field coil. Okay. Now one more thing is like basic KVL KCL I will apply. So of course for a generator, right, the machine will supply the current. That's why IA, load current, is going into the terminal. And for a motor, I am supplying the electrical power, and in the output this motor is rotating. Correct? The prime mover will rotate and I will use it for my own purpose, right? Very basic thing. So that's why the load current is from the terminal to the motor because I am supplying the electrical power, and here it is from the generator machine to the terminal because I am generating the electrical power. Okay. So now very basic thing, very basic KVL. What will be the terminal voltage? Terminal voltage will be the generated voltage minus the drop across the armature resistance because all the coils will have some resistance. I will derive the expression as well of armature resistance later on. So basic KVL KCL I am applying. So it will be EG minus IA into RA. Okay. And in this case, what will be the terminal voltage? In this case, the terminal voltage will simply be V will be equals to EA plus IRA because of the direction of the current. Remember that this is the direction of the current. So drop will be here like this. Here the drop will be like this. Very simple KVL I am using. So this is the motor. This is the generator. Now if you are having confusions, why is it called back EMF, why is it called generator EMF, just for now you can assume this to be the armature EMF. Sometimes in books they write EA as well. EA is basically the armature EMF. Okay, that's it basically. That's it. Okay. Now let's discuss, like this was the first part, that is very easy. Now let's discuss about the separately excited DC machine. In a separately excited DC machine, there will be a field winding that I will excite separately. I will provide a voltage current and I will excite it, and due to that a flux will be generated. And remember, why am I drawing it like this? There is a reason, because in most standard textbooks you will see that drawing is like this, right? This is the field winding and this is the basically the motor, right? Why am I drawing it? There is a significance of drawing it. What is the significance? The significance is I am signifying that my flux, right, in this case my flux always will be perpendicular to conductor, to direction of rotation, right? If it is 90-degree perpendicular, then only the sin theta will be maximum, then only it will be like sinusoidal BLB, then only it will be follow the formula of BLB. That is the thing that I wanted to mention over here. Okay, understood? Great. So generally here also the flux is assumed to be constant only because I'm providing a DC voltage here. So here also the flux is constant. So roughly you can assume that a permanent magnet DC machine and a separately excited DC machine both are the same thing. So a separately excited and a permanent magnet are both almost the same thing only, but just I'm providing a supply here to the field winding. It is a separate. Okay, that is the case over here. I hope you have understood this point. Now few things again, if it's a generator or a motor, what will happen if it's a generator and a motor, right? So if it's a generator, what will be the value? Again, what will be the terminal voltage? V will be equals to Eg, the generated voltage, plus Ia into Ra, right? Now this Ia current is same, right? So what is the output power? Output power is V into Ia. This is the output power, is equals to Eg. If I multiply by Ia on both sides, this will be Eg into Ia plus Ia whole square into Ra. What is this basically? This is the copper loss across the armature. So again, I'm getting back to the same formula, right? This is the copper loss across the armature. This is the input power that I'm providing. I'm rotating the shaft, and this is the input power that I'm providing, right? Input power that I'm providing. This is the output power. Okay. So this is the case basically. This is the thing that I hope you have understood. So we will come back to this later on as well, don't worry. But I want to derive this input power, right, in terms of mechanical quantities, because I'm giving input as a rotation. So I want to derive this in terms of mechanical quantities as well. Okay, so I will come back to this, don't worry. Just wanted to give a brief about separately excited. So the separately excited, there can be two types. One will be voltage excited, where the like winding will be excited with voltage. Construction will be the wire will be very long. It will be thin wire of high resistance. Why it will be thin wire of high resistance? Because the voltage rating will be very high, right? VF will be very high. If the VF is very high, and of course it cannot support very large amounts of current. Okay, I cannot, like, if the resistance is low there, let's say if RF is like almost 1 ohm, and if voltage is VF is 250 volts, right, or generally it is 200 volts, so huge current will flow. IF will be 200 amps. That will be huge current. So we have to add a resistance in series. We have to add a resistance in series so that the voltage is lower. So if I add a resistance in series, then the field current will be lower. IF will be somewhat lower, right? But I need MMF, right? I need the flux, I need good MMF. So what I'll do, I'll make the number, because MMF is N into IF. So now I will increase the number of turns of the field coils. That's why for a voltage excited field winding, the number of turns will be higher. Okay, similar to shunt field winding. Don't worry, I will come back to this discussion again later on. And for a current excited field winding, it will have fewer number of turns, because it is mainly I'm providing a current, right? So again, N into IF will be higher this time, so it will have fewer number of turns, and as it has to support larger current, that's why the cross section area, the area of the winding will be higher. If area is higher, it will be more thicker. It will be thick. So that's why they're telling that it will be thick. It will have low resistance, because already I'm passing very high amount of current. Why will it will have high low resistance? It will have high resistance here. Another point, if the resistance is high, let's say if RF is 1, so what is the power loss? Power loss will be VF whole square by RF. So it is VF square this time. And if the resistance is, let's say, 100, right, it will be, power loss will be VF whole square divided by 100. So power loss will reduce, so the loss will reduce, right? That's why we try to increase the resistance in case of a this voltage excited field winding. And for here, what is the power loss? Because here previously the voltage was fixed, now here the current is fixed. So the power loss will be IF whole square into RF, right? The field resistance, field winding resistance. So of course I have to reduce my resistance, then only the losses, overall losses will reduce, right? I don't want like whatever current I'm providing, I want it to get used for mmf, production of mmf, not for losses. I'm not supplying the current for losses. So that's why I don't want this, right? So that's why the resistance here will be lower. If the resistance is lower, the current will has to be higher. So if current is higher, area will be thicker and number of turns will be lesser, because of course I don't want to go beyond certain level of mmf, right? Because then the core will get saturated. Then the core will get saturated. I don't want that. So that's why here it will carry higher current and it will have less number of turns. Okay, so same thing, same expression for a DC machine. So for a DC machine, it's very simple, right? Sorry, DC motor, it is very simple. The terminal voltage V will be equals to the back EMF plus IRA, right? Because this time I am providing, supply is providing the power, not the generator. Okay, same thing, same equations are written over here. Whatever I have discussed, same equations are written over here. Okay, one more thing, unless explicitly mentioned that the free current or exciting current is varying, we assume flux to be constant for a separately excited, and for any other case to be for a factor of the matter. Unless and until mentioned, the field current will be constant. It is analogous to permanent magnet DC machine, but anyways it is permanent magnet, right? The flux, so flux will never change. Okay, so these are the armature voltage definitions. These are the equations that we know. So there are a few more drops that will happen. Brush voltage drop, internal drop, we will discuss about this. Brush voltage drop we will discuss. So there is a bit of drop in the brushes. So whenever current gets transferred, there is a bit of drop, because there is a bit of current changing, right? So due to that there is some power loss, there is some drop. We will discuss that in the construction portion. Now I want to discuss about a very key point. We got this value, right? We got this value that Eg into Ia was the mechanical power, or Eb into Ia was the mechanical power. This is the mechanical power that was coming out of the motor. In this case, if I multiply here in this equation, if I multiply by Ia on both sides, so this will be Eg into Ia, that will be the mechanical power for a generator, and for a motor this will be Eb into Ia, this will be Eb. Actually this will not be Eg, this will be Eb. Okay, this will be Eb. So how do I quantify it in terms of mechanical power, right? So one thing we know, this is the mechanical power. This is the mechanical power that is getting converted. So this is the power available at the shaft. So this is actually called as the shaft, right? This thing is actually called as the shaft. This thing is called as the shaft. Okay, so these are the values, these are the quantities, that is the power available at the shaft. Now how do I quantify? Because whenever there is a customer, right, a customer goes on to buy a motor, customer does not understand this Eb into Ia, Eg into Ia. You are an engineer, you will understand this. You are an engineer, you will understand this. What is Eb into Ia, what is Eg into Ia? But customer does not understand. Customer understands horsepower, HP, right? Horsepower. Customer understands the speed. All these things, customer understands these things. How fast the motor will rotate, what is the horsepower of the motor, what is the torque, customer understands the torque. These quantities customer understands when they are going to buy a motor. So I have to quantify this in terms of mechanical quantities. So very basic thing, if I have a object block here and I am applying a force, and due to that force it moves by a distance of ds. So what is the small amount of work done, that is delta w? Delta w will be f dot ds, right? This we have been studying since class 11th, right? F dot ds. What is the power formula? Power formula, P equals to change in work divided by the change in time, delta w divided by delta t. So I can replace this here, right? This will be F dot ds, or this dw. Dw can be written as dw upon dt. So this will be F ds upon dt. So what is ds upon dt? Ds upon dt is velocity. So this will be F dot v. This you already know. So this is the force for a rectilinear motion, linear motion. So this is the force and this is the velocity. This is the formula of power for a rectilinear motion. Okay. Can I do something similar for a curvilinear motion? So now if it is a curvilinear motion means rotational motion, right? Rotational motion or curvilinear motion. Yes, like power here as well will be same. Power will be again force into the velocity, but this time in curvilinear the force is actually discussed in terms of torque. So it will be torque, power will be torque, and velocity in this case will be omega, because it is angular velocity. This will be angular velocity now. So velocity will be angular now, and the force will be torque now. Okay. So this will be basically omega into t, omega m into t. So that's how I can quantify. So this is the power available at the shaft. So this is the same power available at shaft, right? So this is what I can quantify. So this will be equals to basically, this will be equals to omega into t will be the generated Eg into Ia, or will be equals to Eb into Ia, because these are the same thing only, power generated at the shaft. So engineers will understand this term, but our customers will understand this. But we are engineers, so we have to understand both, right? Because we have to explain them both. So I hope this formula intuition also you got, how did this formula came up, right? Omega m into t, how this formula came. So I have given you the intuition as well. So what I will do is, today lecture is already gone long, so I will give you few homeworks. I will give you a few homeworks. I want you to try and perform. Let's do the first question. The second question I will do as homework. I will give you as homework. So let's do this first question. A permanent magnet DC motor has an armature resistance of 1 ohm. Okay. So whenever any DC machine question will come, right, either draw the diagram or start writing that data. One of them, either one of them works. So here it is a permanent magnet DC motor. They explicitly mentioned it is motor, right? If they don't want to mention, they will say it is a DC machine. If they don't want to mention whether it is a motor or a generator. Okay. So as it is a motor, it will generate, I will provide the supply, and IA current direction will be coming from the supply to the motor. So this will be the EB, and IA I will provide from the supply to the motor, right? And your motor will rotate basically. Your motor will rotate. Okay. Now I will clarify one more thing just quickly, right? So they have given RA is equals to 1 ohm. So your armature resistance is 1 ohm. Okay. Okay, it is a permanent magnet DC motor, right? So it does not matter. I will not draw this, right? So armature resistance I have to draw. Okay, I will just bring the first diagram. What is the first diagram? Yeah, this one, right? So this is the diagram. So RA in this case is 1 ohms. Okay, sorry. RA in this case is 1 ohms, and IA current I don't know, and the supply voltage, right? They're telling the supply voltage is 150 volts. So this will be 150 volts. Okay. And what are they telling? And generates an induced EMF of 50 volts. So the DC motor has generated an induced EMF in the motor to be 50 volts. So EB is equals to 50 volts. They have already told me. While operating at 500 RPM. So it is operating N equals to 500 RPM. So you keep on write down the data. If the armature is connected to 150 volt supply, the starting current will be what? When the motor is rest. So initially when the motor is at rest, right, the motor is not rotating. So for the case 1, the speed is 0, and I have told you what is the induced EMF. It is proportional to flux, it is proportional to the speed, it is proportional to the number of conductors, it is proportional to the number of poles. So if speed is 0, motor is not rotating, it is at rest, right? It is just like the case 1 where the motor, case 1, yes, case 1 where the stator is providing some field but motor is not rotating. If motor is not rotating, there is no rotation, so there will not be any induced EMF. So in starting, right, starting, the induced EMF will be 0. Induced EMF will be equals to 0. Okay, now next, so in starting, induced EMF is 0. So if induced EMF is 0, this circuit can be like, what is the electrical equivalent of this circuit? The electrical equivalent of this circuit is something like this. So this is my supply, DC supply, just simple KVL and KCL. DC machine is just about KVL and KCL, right? This is my back EMF, this is my supply voltage, plus minus, this is always constant, 150 volts. RA they have mentioned as 1 ohms, and EB is the induced voltage across the motor. Okay, EB is the induced voltage across the motor. So from here I can directly write what is the current, starting current, I starting, right? I starting will be what? I starting will be equals to this simple KVL case, right? EB is 0, it is V minus EB divided by 1 ohm. So EB is 0 in starting, so it is 150 by 1, huge current, 1. So as the motor will rotate, there will be an induced EMF in the motor. Huge current is flowing. Due to huge current, what again? Now it is the case 3 where there is current in the rotor and in the stator. So again, due to the interaction, motor will rotate. Slowly motor will rotate, hence induced voltage will be there, hence the armature current will reduce. That's why it is called as back EMF. Because why it is called a back EMF? Because this is opposing the change, right? Opposing the change in magnetic field. Because a current instantly is flowing, opposing the change, right? That's why it is called back EMF, because this EMF is opposing the change. Slowly this EMF will increase and current will reduce, right? Because motor is rotating. If it is rotating, induced EMF will be there. Higher, with higher speed, higher the speed, higher the induced EMF, because it is directly proportional to the speed. Induced EMF is directly proportional to the speed. Now what are they asking? The induced EMF when the motor reaches 1000 rpm. What will be the induced EMF when the motor reaches 1000 rpm? So I know one thing. So this case 1 is solved. This is the answer, right, for the case 1. Case 2. Case 2 is basically when n is 1000 rpm, what will be the induced EMF? I know my EMF, induced EMF, is proportional to flux, number of poles, number of conductors, and speed. So all these things are constant, right? All these are constant, just I am changing the speed. So I can write the induced EMF in case 2 divided by induced EMF in case 1, right? The ratio will be basically N2 by N1, right? So from here I can directly write what is E2 equals to. E2 is equals to induced EMF in the case 2, N2 is 1000 rpm, divided by N1. N1 is the, when my speed was 500 rpm, the induced EMF was 150, the induced EMF was 50 volts. So this will be when it was 500 rpm, the induced EMF is 50 volts, right? So this will be 2 into 50, that is 100 volts. Okay, so again same, very easy question, right? Very easy question. So in DC machine, trust me, very easy questions will come. You will be able to solve it. Just a bit of armature reaction, all those things are there that we will discuss. So this was the solution for this question. 100 volts is the answer and 150 amperes is the answer for case 1. So I want to leave you with the second question. This is the gate question. I want you to solve this question, and in the next lecture we will try to solve this. This is the question, and this is also another question that I want you to solve. Two gate PYQs I want you to solve. So in the first lecture itself, you will be able to solve all the gate PYQs. I mean, this whatever we have learned till now, okay, those you will be able to solve. So that's how the flow of lecture works in PrepFusion. Okay, so these two lectures, these two questions I want you to give you as homework, and in the next lecture we will solve these questions, and we will understand more types of DC machines like shunt, then series, all those things we will understand. So I hope you have enjoyed this lecture. If you did, make sure to comment down below, make sure to like the video, make sure to comment on the first video of this playlist. Really will help us out. Thank you, and I will see you in the next lecture. Until then, happy learning.